So let's talk a little bit more about binomial distributions. So let's talk about the expected value and the standard deviation. Now remember, the expected value is the same thing as the mean, and the mean is just n times p, so it's the number of your sample size times the probability it occurs. And you'll see in this problem here, my example, how really expected value makes complete sense. But let's think about it for a second. If I define success as getting heads on a coin flip, and we know that probability is 0.5 or 1/2. If I ask you, if you flip a coin 10 times, how many times do you expect heads to come up? I think 10 times, probably half, so 5. So same thing would be if we took the 10 times the 0.5 for our probability of getting heads, and we'd get 5 also. So expected value makes sense. Standard deviation, honestly, write it down, look at it, use it on a 3x5 card on the test. There's no logical way I can have for you to memorize standard deviation for a binomial. It's just the square root of NPQ. That's it. So let's look at this problem here. And it says the probability an egg is rotten is 0.3. Okay. Find the expected value and the standard deviation for 10 eggs. So expected value is easy. You know what? I'll pause for a second. So if you want, you can work out expected value and standard deviation, and then we can compare our answer. So I'll pause for a second. Okay, so expected value should be n, and again, remember, make our shopping list. We're going to need n's, p's, and q's for this adventure. So n is our sample size, which is 10. P is the probability of success. And here we're defining success as a rotten egg. And that's 0.3. And then Q is 1 minus success. So 1 minus 0.3 is 0.7. So the expected value is n, which is 10, times 0.3. And that's our mu. This equals 3. So if 30% of the eggs are rotten, we have 10 eggs. It makes sense then that we would find that 3 of them are rotten. Okay, so now our standard deviation. And it's the square root of n times p times q. I'll fix that. So n times p times q. So this is the square root of 0.21. Square root of 2.1. Oops. And let me do the calculator real quickly here. I get 1.44914. So that's your expected value, or your mean, and your standard deviation. Okay. Sometimes binomials get really big. So we want a normal approximation to a binomial. Notice the word approximation. It's not exact, but it works pretty well. And there's 2 conditions. First of all, it has to be a binomial condition. This is bins. So we have to verify each letter in bins. Oops. And second, n times p is greater than 10, and n times q is also greater than 10. That's 10, not 1. Just write 10. When we do that, we approximate it as a normal distribution, NP, that's my mean, and standard deviation. Okay, I'll give you a second to write that down. So let's look at a practice problem, how to apply it. So you can read, so I won't read this to you, but I'll give you a second to pause the video and read it. And I'm going to go on with the problem, so I'll give you a second. Okay, so you should have been able to read the problem in that time, and I'm going to fix this really quickly right here. There we go. It says that we need to determine, is this a binomial? So we'll make sure it fits bins first. So we're going to verify our conditions. Whenever we say we can do something, we're going to verify our conditions. So we have bins. So first of all, the B, is this a binomial? Is it success or failure? Yes, it is. So success is defective, failure is not defective, and those are the only two situations. So I'll say defective or not. I, are they independent? It seems like they'd be independent, but we don't know for a fact, but there's nothing on here that says one tire influences the next. So for this we can put PWC. That's proceed with caution, which means we're pretty sure if something comes up and says it's not independent later on, we'll let you know. N, is my sample size fixed? Yes, it is. It's 1,600. And is my probability fixed? My probability of success? It is. It's 0.08, which is 8%. So it meets a binomial condition. Is NP greater than 10? Well, let's see. Let's make my shopping list. I need an N, P, and a Q for right now. So let's see. N is 1600. P is 0.08. And Q is 0.92. So let's find out what NP is. So if N is 1600, NP is 0.08, and we need this to be greater than 10. We'll see if it is. So let me use my calculator here. 1600 times 0.08, and I get 128. And then 1600 times 0.92 is certainly much greater than 10, but we can kind of verify it. If 128 of the 1600 are success, that must mean the remainder of them, which is what, 1472, are failure. So, does this meet the second condition? And in fact it does. I'll change the color here so you can see me check these off. Binomial, and it meets this. So now we can use a normal approximation. So now this is normal. My NP, which I did right here, is 128. And my square root of NPQ, I can do the calculator. So I have 128 times 0.92. I have 117.76, and I'll take the square root of that. And I get my standard deviation here is 10.85, and I rounded it to 2 decimal places. Now, since this is now a normal distribution, I can use my one normal formula, which is x minus mu over sigma. And my test point is 150 or fewer. Make sure I write that down. P, x is less than or equal to 150. So filling this in, I have 150 minus 128 over 10.85. This is equal to 22 over 10.85. And we can do a little mathy stuff on the calculator. 22 divided by 10.85. I get 2.03. Alright, so let's find out what does that mean. Let's look at our z-table. Those are negative and our positive, 2.03. .97882. So 0.9788. Come on now, there we go. So what's the probability? P equals 0.9788. Hope that helps you some. Just so you know, this is the last video on binomial. The next video will be on geometric.